Hi, everybody. Welcome to what I think is the sixth video in this series on R. Um, so we've covered a lot of ground in the last five videos. We've talked a lot about different tools for cleaning data, for filtering rows, making new columns, plotting stuff. We've talked a little bit about like statistical tests like regression, what they are, and how to do them in R as well. Today, we're going to kind of take a bit more of a macro view and talk about like organizing our code in efficient ways that helps us do things more quickly and make fewer mistakes. So that's going to take a couple of different forms. I'm going to first just kind of like walk through how I try to just set up my projects from the start and kind of talk through some of the reasons why I do it the way that I do. And then I'm going to talk a little bit about moving from kind of the folder setup um, to the actual code. I'm going to talk about how I organize um, a single R script and some ways, some things that I think are really important when you're thinking about what should be in my R script and how it should be set up. And then kind of we're going kind of from the most macro kind of down further and further. We're going to talk about some specific coding things that you can do to make your code more efficient. And in particular, we're going to talk about how you can do something like, for instance, let's say you have to read in 100 different CSVs. You know how to do that in 100 lines of code, right? You could just do read underscore CSV, copy that a bunch of times, and assign them all to their own objects, etc. And then you've loaded them all into R. But that's 100 lines of code, and there's a lot of room for error in that approach when you're copying and pasting a lot. That's usually the time when errors can really pop up. And so I'm going to talk about how you could do something like that in one line of code rather than 100 lines of code to really make things a bit more efficient. And then if we have time, we might talk a little bit about writing our own functions. Right now, we've only been using functions from R or from R packages, but we can also write our own functions, and they can often be really helpful in kind of streamlining our code. So that's the plan for today. So to start, I just kind of want to talk through how I set up the code for my dissertation. So if you're in my UROP group, you know that my dissertation is about turnover in US state bureaucracy. So I'm collecting all this data on state personnel, going state by state and collecting their personnel files. And then eventually I'm going to merge that to voter data. And so there's a ton of data flying around because I'm collecting data from 50 different places, and each state's data is messy in its own way and needs to be cleaned and standardized, etc. So there's a ton of code, there's a ton of data, and there's a frightening number of ways in which I could screw stuff up. So I'm going to talk a little bit just kind of about how I organize that in ways that I think just reduce the opportunity for me to make a big mistake. So everything about my dissertation is in this state bureaucracies folder. And you'll see here that I've separated stuff out. So some of this stuff is code, other stuff is not. I have all my actual code, so the R scripts, the .r files, are in their own code folder. There's no data. There's no data in this code folder. It's just our scripts. And then I have this separate data folder where all of the data lives. And there's different types of data, which are demarcated here. And so state employee data is the most relevant for what I'm doing right now. These are all of these state personnel files. And you'll see that I broke them all out by state. So let's look at Connecticut. So these are going to be the personnel files for Connecticut. And I think this is a really important step here. You'll see that within Connecticut, so it's just personnel files that are applied to Connecticut. And then within that folder, I've separated it out even further. And I have one folder that's just the raw data, just the stuff that I got straight from the state. I don't change this at all. I never overwrite this. I only read this in. And I think it's super, super helpful and important when you're setting up your own projects to have whatever your raw data is, your inputs that should never change, should be in their own folder called raw or something like that, so that you know that you shouldn't overwrite them. Because the last thing you want to do, which totally happens, I did it once accidentally. Thankfully, it wasn't a big deal. But the last thing you want to do is write a script where you pull in your raw data, read CSV, etc. You do a bunch of stuff, you clean it up, and then you write underscore CSV and you write it back to your computer as a CSV file, but you assign it the same name as the input data. In that case, it's going to be overwritten and the input data is going to be completely erased. And this is why everything you do should be backed up by like Dropbox or GitHub or some sort of version control. Because if it's not, you just lost your input data and your R script you just wrote, you better have gotten it right because you can't go back and change anything because you don't have any more input data. Your input data has been erased and is now your output data. So it's really important to separate out your raw data, your inputs from your outputs, which in my case, I'm calling clean. I don't think I've done this yet. Well, this is very wrong, but this is going to be once I merge it with the voter files. So I think a general theme here, in addition to separating out clean data from raw data in their own folders, is do not be afraid to use a lot of folders and subfolders. I think it's insanely helpful as a way to organize things. It doesn't make anything more difficult. It doesn't make doesn't slow anything down at all. It means your file names are a little longer, but that's fine. But it just so helps in keeping everything clean, standardized, and you know where things are. So I also have the exact same setup in like South Carolina. I have my raw folder. This is everything straight from the state. And then the clean folder, the outputs. Once I run a bunch of our code, and then I save it back into this clean folder. Okay. So that's on the data side of things. On the code side of things, I also think it's helpful to think about, I think it's really, really helpful to think about your code as each script should do one task. That might be a big task, it might be a little task, but it should do one task. And that means that you might have 5 different scripts that do 5 different things rather than one big script that does one thing. But when you do those in those separate ways, I think it becomes a little bit more manageable to kind of trace errors from one to the other and also just organize your files a little bit more. I don't know, like the computer sciencey people might have different views on that, but I find that to be a lot more helpful than to write one big script that does everything. So for instance, when I'm cleaning these personnel files, it's quite an operation to just, well, in some states, it's quite an operation to just clean one. The raw data is a mess, and I have to do a lot of cleaning before I can even think about merging it with voter data or doing any type of analysis with it. So basically what I have to do is, and in particular, the major issue I have is states aren't giving me in few cases, states are giving me unique employee identifiers. And one of the things I want to be able to do is track employees throughout their tenure in the state workforces. And if you have a really unique name, it's pretty easy to see. It's pretty easy to see how you enter, stay in the workforce, and then exit. But if 25 David John Petersons work for the state, it's really tricky to figure out which David Peterson is which. And when one leaves and then comes back, like, is that the same David Peterson who just left earlier? Or is it some other David Peterson? And so the main cleaning task I have to do is try to assign unique identifiers to my employees. So that's kind of this big task. And so I've kind of structured my cleaning in 3 steps. I have this initial first clean where I just standardize everything. I make sure that all my variable names are lowercase with underscores. I make sure all my character variables are have no uppercase letters. I make sure my date variables are in the right format. I parse the names. So if they give me the names all in one variable, I pull out the first names, the middle names, the last names, etc., the suffixes. So I just try to create this standard file. With that standard file, I use this package called FastLink, which I don't need it's not relevant here, but it's this R package that does this very fancy probabilistic assigning of unique identifiers to people. And then I take that output and I do some initial extra post cleaning to get some more unique identifiers and to kind of make sure it's as good as it can be. So there's kind of 3 steps. There's the initial clean, there's this probabilistic assigning of IDs, and then there is this post assignment additional cleaning. And so what I've done is I've structured those, I've made the R files represent those 3 different steps. So all of my cleaning is happening in this clean-personnel file. And you'll see that I've broken it out into these 3 folders. So this is that first step I mentioned. This prob-unique-IDs is the probabilistic assigning of IDs. And then this is the after-the-fact cleaning. And you'll see that in here, now I have scripts for every state. Every state gets its own script for the initial clean. This is just the initial clean. You'll see that if I open one of these and we look at it, it pulls in the raw data. We'll talk later about what this does, but just bear with me. This is pulling in the raw data. And then it's saving this raw data here that the second cleaning file for Arkansas can then use as its input. Oh, wait, you all didn't see that because I was on my other desktop. Oops. Apologies. Let's do that one more time. So here's the Arkansas cleaning file. So this is just the first step of cleaning Arkansas's personnel file. It gets its own R script. And I'll talk about this more later, but this is going to read in the raw data. So this is in the AR-raw data file folder. And then its output, it's going to write this as an output. And this is going to be used as the input for the second step, which is the probabilistic assigning of IDs. And so then I go to the second step. And the second step also, each state gets its own script. So here's the Arkansas one. And you'll see this was the output from the AR-clean, the first step in cleaning Arkansas. So I'm reading it back in the second file. And then this is going to probabilistically assign all these unique identifiers to people based on variables available in the Arkansas data: gender, first name, last name, middle initial, ethnicity. So I run this. Actually, I run it on this like University of Michigan supercomputer, but that's not applicable here. Just imagine I run it on my own computer. And then the third step, and the same thing is happening here. Arkansas gets its own R script for the third data cleaning task. So this is going to read in the output from the second step as its input, do all this additional cleaning, and save this cleaned Arkansas file from 2019 to 2022. Amazing. So I think the key thing here is that I have not and again, everybody does this differently, but I think it's super helpful for me to treat every state differently. Every state gets its own scripts. I am not trying to do Arkansas and Louisiana in its own script. That would be mind-bogglingly hard in my head. So each state gets its own scripts. And then furthermore, within that, each state's step gets its own script. I'm not trying to, in one R script, do step 1, step 2, and step 3. In my case, that would actually not work at all because I have to use this supercomputer. But even if I didn't, I think that's just too many different things happening in one script. I'm trying to have each script do one task, and I'm defining those tasks as this first step, second step, and third step. And so whatever the idea of what a task is all relative to your project. But I think the idea of having multiple scripts that are each doing their own separate things is, again, I think a useful thing to think about, rather than trying to, which is something I often see, which I used to do as well, trying to do every single thing from initial data cleaning to final plots in one very, very long R file. I think that, at least for me, I find that leads to me making mistakes. Okay, so that was kind of a macro, just like some tips on organizing our projects. Let's go down and talk about how to organize a script. And so do I have I don't have the project open yet. Okay. Let me open from the project here. This other R script window. Okay. So let me close this Zoom thing, video panel. Nope. Meeting controls. There we go. Okay. So you might have already done this, but if you haven't yet, I want you to go to Tools, Global Options. And I want you to set your workspace features to the same as mine here. I do not want you to restore your R data into workspace at startup. And I want you to never save the workspace to R data on exit. What does this mean? This means that when you close RStudio and you reopen it, it is going to reopen it with an empty environment. Okay? Now, this might cause some short-term frustrations because it might be, and this is totally normal when you're learning, that you're writing a bunch of stuff and you're kind of treating this environment as like the permanent feature of what you're doing. Like this is kind of what is lasting from my R code. Like this is kind of the permanent thing. Or you could be like, I had a student last year who was doing her honors thesis in R and just kept R open for like 2 months. But then something failed and she had to restart R, and then we had to like figure it all out. So don't do that either. But I want you to set it up, again, through those global options so that this is going to open clean. It's going to open empty when you reopen RStudio. And the reason I want you to do that is because what I really want you to think about as the permanent thing that exists here is not the objects in the environment. These are all temporary things. These are not lasting. These are not lasting. These are not permanent. What is lasting is the words you write down in the R script. That is really the the reproducible, again, permanent thing that you're saving and adding to. Okay. And so with that, that means that when you write an R script, you want to be able to close R, you want to save your R file, close RStudio, and be able to reopen it and get to the same place in R that you were before you closed R. So what do I mean by that? Let me show you. This is my, let's do Mississippi. So this is, let's not worry about, there's a lot of code in here that we haven't really talked about, but that's okay. So let me see, what's the best way to think about this? So when you're thinking about the code as the permanent thing, it means it needs to be able to be quickly rerun and to get you back to the same place. That means that you need to order stuff sequentially so that, because R runs everything from the top down, from line 1 down, right? So you can't have a script where you have to run line 4 in order to run line 2, okay? What you don't want to do is do something like this. This is going to cause you problems, right? Because if you run that, it's going to be like, I don't know where X is. And X is right here, right? And you might say like, okay, fine. But like when I'm actually doing this, I'm going to know, like, I'm going to run this part first, and then I'm going to go up here and run this. And then I also forgot to define Y, but let's just say I have Y6 here. And I define that too, yada, yada. And like now it works, fine. But this is kind of where the rubber meets the road in terms of like building stuff that's reproducible. This is great when you remember all the steps. When you're in an R file, you remember all the nitty-gritty details. But if you're working with other people, or what's much, much, much more likely is imagine your future self as another person you're working with. Imagine your future self as like this separate co-author who you need to be nice to, right? Future you is not going to remember all these steps. Future you is going to want to be able to open an R file and just run it straight through, and it's all going to work, right? So that's really how you should try to write your R scripts. You should write it so that line 2, you have to run line 2 to run line 3, and you don't have to run line 4 to run line 3. It should be sequential. So what I want you to be able to do, is I want you to be able to open a file like ms_clean, Command A, and run it. So I just selected all the code and I'm running it. It's going to take a minute because there's a lot of things going on here in Mississippi. But the point is that your code should be able to be open and just ran. You shouldn't have to fiddle with it. It should just be able to go. And maybe it's not completely done yet, and that's okay. But like, even if it's something you're still working on, you should be able to close it. You should be able to close it, reopen it, run everything you've done, and get right back to the place you were before you shut it down. So you'll see that everything ran just like that. A way to kind of help you kind of get in this habit is to always be running stuff and then restarting R. So you can restart R without closing it. On a Mac, it's Command Function Shift 0, which is a doozy. So you see it just cleared out the environment. It also just cleared out any packages I've loaded, so this isn't going to work. So I have to reload everything. And you can also exit that out. So now I have a totally clean thing again, and I could just run it all again. And this is a helpful way to make sure you don't have any weird things going on. You don't have any, again, like line 4 being necessary to run line 3, stuff like that. So a helpful way to kind of get you in this habit of writing code that can be open and ran. Okay. Other thing to talk about, I think, briefly, is like when you're writing code, it's really helpful to write notes to yourself. Again, imagine future you as your co-author. You want future you to be able to look at this code and understand what's going on. So I just have a little description up here at the top. And then I have these little guys here that's just kind of breaking it out. So actually, if you use 4 hashtags, 4 pound signs in our studio, it'll kind of create it as its own little chunk. So you could actually just like go like this. So you'll see here's the 1, 2, 3, 5 chunks that I have, each of them doing this own separate task. So I'd encourage you to write little notes to yourself, especially if you're doing something that's like odd or tricky that you know you're just not going to remember. I think another helpful tip when you're commenting out code is try to and I don't do a good job of this, so I'll be the first to admit that I'm not always great at this, but try to write why you're doing something rather than what you're doing. And again, I don't have good examples here because I don't do a very good job of this, but I do try to shoot for it at least. But the what can usually be, you can, if you're filtering out people, maybe you have some like outlier value that you want to filter out. Like it's easy to see what you're doing by just reading the code. Like you're filtering out these values. But it might not be clear why you're filtering out those values. And if it's some weird thing that, again, future you is not going to remember why you're doing that, it'd be helpful to write a little note, like filtering out outlier values because they're not applicable because of yada, yada, yada. So just another tip there. Okay. So that was, okay, so we talked about organizing projects. I gave you some tips on organizing your scripts. Now let's talk about some code, some things you can do to write more efficient code. So let's see what's the best way to do this. Let me just use restart on. Okay. So I gave the example off the top of like, let's say you have to read in a lot of files. This is something I'm doing a lot with my personnel files. Some states are giving me, let's see if I can find one off the top of my head. Some states are giving me each file separately. I think Oklahoma does this. Yeah, perfect. So Oklahoma is giving me all the CSVs for each quarter as their own document, right? How many are there here? 50. 50 CSVs. So at this point, you know how to read in these CSVs. You know how to read in these CSVs in 50 lines of code, right? You can do something like this, and then you could do read CSV file 1.csv. And then you can copy and paste and change this to this. And then you could do this. If you want to get fancy in RStudio, you can also, on a Mac, it's the Option button. If you hold down the Option button, you can get this mega cursor. And so you could do something like for read underscore CSV, file for.csv, but you're still gonna have to go through here and do 5, oops, and then 6, 7. And not only is this gonna take a long time, but like, just think how easy it is to make a mistake. So I made a mistake here. What I'm calling 5 is file 4. It's the same as 4, right? That's a really easy mistake to make. Very easy. When you're copying and pasting, that's where errors can really happen. And again, like, this is only 7 files. Imagine if you're doing this for 50 or even more. So this is a great place to think about how you could reduce the amount of copying and pasting you're doing. Usually, if you're copying and pasting 3 or more times, there's probably a more efficient way to do it. So in this case, what we're going to talk about is we're going to talk about how we could iteratively read in CSV files, store them all as one thing, and then mush them together into one big data frame. And this is one instance of kind of this general phenomenon called loops, or iteration, something like that. In other programming languages, these are much more central. For loops are something that you learn, like, if this was a different programming language, like, we probably would have done for loops on like video 2. In R, they're less central because you don't have to do them for a lot of basic tasks, because the iteration is kind of built in. So for instance, let's say I want to test whether 2 equals so if I run this, it's going to return false, false, true, false, because only the third value in this vector is equal to 2, right? But under the hood, what is this doing? Under the hood, this is saying, take 2 and test if it's equal to 1, and then return that true or false. And then take 2 and test if it's equal to 3, and return that true or false. Then check if 2 is equal to 2, and then check if 2 is equal to 4. So in many other programming languages, you would have to write this in a much more complicated way, in terms of this loop, where you would actually have to explicitly tell the language to loop through each of the values in this vector and test whether it's equal to 2. But in R, that's just built in. It's vectorized. It's just built in that if you do something like this, R is going to know that it wants you to test. It doesn't want you to test whether 2 is same as the vector 1, 3, 2, 4. It knows that you want to test whether 2 is equal to the first element of this vector, and the second element, and the third element, and the fourth element. Okay. So that's why we haven't done them yet. But loops, iterations, stuff like that is insanely helpful for other tasks in R that don't have this built-in vectorized format. And one of them is reading in a bunch of files. There's a ton of other examples. I think this is probably the most concrete, and the one that at least I use this for, like, day in, day out. So I made some fake CSV files for us to practice on that are in the video. So in example dash data, there's now a practice underscore CSVs. And these are just like fake data that I made up, kind of based off the idea of the personnel files. So we have these people, we have their salaries, and then we have this year. The person and the salaries aren't changing, but you'll see that the files change from 2010 to 2011, 2013. And the year column changes correspondingly. And so what do we want to do? We want to read in all of these files and then create one data frame where all of these separate data frames, these separate CSVs, are just binded together in one thing, right? And again, this is a task that I have to do all the time. So let's just think about what that would look like. Let's see where that lives. That, for me, is going to kind of be a little bit of a ways away. UROP, ROP shared, videos, example data, practice CSVs. We're getting there. 2010 data. Sweet. All right. Bit long. Cool. Okay. So we read it in, right? Here it is. We know how to do this. And, right, we know how to do this by copying and pasting a lot, right? You could keep doing this for all, however many there are, 12 or so. Yep, we read them all in. Cool. But there's a lot better way to do this. And kind of the key thing here to think about is there's something in here that's changing for each file, while the rest of it is staying the same. So the file name is changing, but the function we're using isn't changing at all. So what if we thought about, just like how we were kind of thinking about with that 2 equals those elements of the vector, what if we thought about trying to write code that did something like take the 2010 CSV file path, this, and pass it into read underscore CSV and return the output. Then take the 2011 CSV file path, pass it into read underscore CSV, and return the output. Then do the same thing for 2012. Loop through each of these file paths and pass them to read underscore CSV and return all of the respective outputs. So that's what we want to do. So the first thing that we need to do, if we want to do that, is define our inputs, which are going to be all of these file paths. And so the file path for this one is this. And so the way to do this is there's this list.files function, which is going to return so this returns all of the files within a given folder, in this case, the practice underscore CSVs. Now we know that this isn't enough for my case, because if we just told R to look for 2010 underscore data under .csv, it would look for those files in my code folder of state bureaucracies, which is not where they live, right? They live here. So we have to do one more thing. We have to create this paths object, which is going to be the concatenation of this and this. What does this look like? This is what we want. So this is this and this and this. Okay. So now we have our input. We have each of these file paths that we want to pass to read underscore CSV iteratively and return the output. And the key function here that we're going to use is called map. M-A-P. This is from the tidyverse package per with 3 R's. And what does this do? This is going to map each value in some input to a function. So what are our inputs? Our inputs are going to be the value in paths. And what is our function? Our function is this. So there's a lot going. This is 3 words, a comma, and 2 parentheses, but there's a lot going on here. And it's probably going to be easier to see once I run it to see what's going on. But this is saying, take each element in paths. Remember, paths looks like this. Take this element and pass it as the first argument to read underscore CSV. The more explicit way to do this would be to use a tilde and actually define it like that, where the period is saying where is the input, is the element in paths going to go in my function. You can also just not think about that in our case, because since we're just passing it to the first argument, it doesn't matter. So that we can just write it like this. So take each element in paths and pass it to read underscore CSV, and then return the output. So you just saw a lot of stuff just happen down here, right? I saved it as CSV underscore out. So it's been saved as a list. I don't think we've talked about lists yet. Lists are the most flexible data object in R. Lists can be a whole bunch of different things. You remember a data frame is a rectangle where each of the columns have to be the same length. A list could be like the first element in list could be the string cat. The second object in a list could be a data frame with 1,000,000 rows. And the third object in a list could be the number 2. Like super flexible data structure. But in this case, what have we done? We have saved all of our outputted CSVs in one list. So here is the 2010 CSV. It's the first object in CSV out. Second object is the 2011 one. Why is the first object the 2010 one? Because the first element in paths is the path to the 2010 CSV. It took the 2010 CSV path, mapped it to the read underscore CSV function, returned the output, took all of those outputs, stored them as a list. Okay. So this is, I'm hoping you can see how this is ridiculously helpful. There are ways to screw this up, but it's a whole lot harder. And think about how flexible this is. If you were to put in like that Oklahoma example, if you were to hard code reading in each of those 50 CSVs, if you added another CSV in there, you'd have to remember that and go to your code and read in the 51st CSV. With this code, that 51st CSV is going to be automatically added when you rerun list.files. So it's automatically going to be added to paths, and it's automatically going to be read in here. Okay. Now, the last thing though here is we don't want this as a list, right? We want this as a data frame. So we can do that by taking CSV out and using this bind underscore rows function. Like that. It's taken that list, binded them all together. Now, this can get dicey if you have different variable names, all that sort of stuff. It can also get weird if you don't have your if you don't have so in our case we had the 2010 variable, we had the year of the CSV file in the actual files because of this column. But like imagine that this didn't have that year column, you would have to kind of recreate so you could know was person A in 2010 or 2012. We're not going to talk about that right now, but just something to keep in mind. Basically, you would just have to assign names to CSV out, which I like to do based on the files. And then if you run that, you're going to get a CSV out that looks like this. So now it has names. And then when you're binding the rows, you can do dot ID equals ID. And now you're going to have this other column that's going to contain the name of the list, the name of the object you read in as a variable, which again is redundant in our case because we have this year column. But I'm hoping you can see that if we didn't have that year column, this would be crucial to know whether this row for person G corresponds to 2010 or some other year. So I said we weren't going to go over it, but then I just went over it. Oops. Okay. So we've read in a bunch of CSVs. So again, I'm hoping you can see that that's a super helpful place where like an iteration makes a lot of sense. Now, this is one of many places. I think this is a great example of this, but there's a lot of other places where you might want to use this. So for instance, maybe, so let's take our example of empty cars, this cars data set. Let's look at it in a little better format. So here's our cars data set. Let's say we want to take the mean of every column in here, right? Mean empty cars, MPG, mean empty cars, cell, mean empty cars, disp. At this place, you should be at this point, if you're writing this, you should be thinking, there's a better way to do this. And that's because we have the same function with different inputs each time. And that's a clue that like you could probably do this with a map statement. So in our case, we're not going to loop across path names. We're going to loop across columns in a data frame. And the default here is if you just provide map with a data frame, it's going to know you want it to loop across the columns. And so let's say we want to do this. And now we have returned all of our means, right? One line of code rather than like 15. So a couple more things and then we're going to call it good. In the above example and in this example, we've returned our output as a list of our results, right? This is also in a list format. In this case, though, we might want to return our output as a vector. Let's just return it as a vector of numbers, the vector of means. We can do this by just changing the map argument to map double. Double means number. It means a double precision floating number thingy. Don't worry about it. Just think if you see double, if you see DBL, that means it's a number. So you run it like that. Now it's returned it as a vector. All we had to do was change which kind of iteration, which flavor of map we're using. Okay, last thing I want to talk about is we don't have enough time to really give custom functions their own justice. But you could also think about like, okay, here we're using mean, but maybe we want to know, let's just make up an example. We want to know mean plus 2, right? There isn't a built-in function that's going to find the mean of a column and add 2, right? We need to write that ourselves. And there's different ways we could do that. But in this map statement, we could actually just write it as its own thing. We could do map double. And now, since we're writing a custom function, we're going to have to bring in this tilde. And so now there's more going on. We're telling this is what we want to do. We want to take the mean of something. This something is denoted by this period. It's kind of this placeholder. Take the mean of something and then add 2. The tilde is just kind of a syntax thing to tell R that we're making a custom function. So the mean of something and then add 2. Oops. What is that something going to be? It's going to be each element in empty cars. So you see we had 20 as the mean for miles per gallon. And then down here we have 22. So it's taken all the means and added 2. Okay, so that's it for today. There's a lot more to say about custom functions. If you're curious, the R for Data Science book has a bunch on them. The idea here, though, is that you could do something like you can define a function like this. Do it input plus 2. I keep saying I'm not going to do stuff, and then I do it. Sorry. But now we've defined our own function called my_function. It takes an argument called input, and it adds 2 to that input and returns it. So now if I do my function 5, it's going to return 7. So that's just an idea of what a custom function is. Ridiculously helpful, can also streamline a lot of code and reduce copying and pasting, and can be used, any function can also be used in this map setup, which when you start working with custom functions and iteration, you can do very complex tasks very efficiently, and just really reduce the time and the opportunity for mistakes. Okay, so I hope all these pointers were helpful. Until next time, thank you very much.